Oh, now I think that's working. I think that's recording. Okay.
Yes, working now.
Oh, thank you. Thank you so much. So we come back, and here we can see some pads, some aggregates that are vertically elongated, but they are different from the prismatic because they are not flat, but they have a concave top. Okay, so they have a little slope here formed by clay eluviation and a creation of a clay deposit here. Okay, so this kind of structure, they show us that we have clay eluviation in that area, in that landscape. So we have something that helps the clay migration through the soil profile. They are different from only the prismatic ones, that we don't have clay elevation. We don't have migration of clay from the surface horizons into the subsurface horizons. Okay. We also saw the platy structure, that are structures formed by sedimentation. So they are by river banks, rivers, and alluvial fans, marine terraces, something of geomorphological process that helps to add material in that area. We saw the structure-less bed that are single grain or single grains. They are typically from soils or horizons that has a sandy texture, that there's a lot of sandy here, and they don't favor the creation of beds of aggregate because sand has a low surface. So low activity surface, specific surface. So they don't favor creation of aggregate because they don't help the flocculation and cementation of particles. Okay. And we can saw this in the massive structure too. The massive structure are structures that we can't see a organization of the primary particles. So sand, silt, and clay are not organized in pads. They are just together, and they start an incipient process of individualization in pads like this. So we can't see an aggregation, or just cracking, and start the formation of pads. Okay, they are typically to sea horizons. Okay, beyond the description of the type, of the shape of a structure, we should describe the size of this structure. So we have some classes, size classes here, and we should classify the structure according to the size of this structure. And we use different criteria according to the type of this structure. So if we have a granular or platy or prismatic or columnar or subangular or angular block, we should use different criteria. Okay, and according to these criteria, we will classify the structure between very fine or thin, medium, coarse, very coarse, or extremely coarse. So we just need to measure the thickness or the diameter of the material, of the structural unit size, so the pad size, and according to the pad size, we should classify this. So if you have an angular block, something like this, we just need to measure the size of this material. Okay, they have something like 2 or 5 millimeters. So we have 3 millimeters, and so we can see that 3 millimeters, something that has an angular block structure and has less than 5, it's classified as very thin material. So we have a structure that has an angular block type, shape, and we have a very thin or very thin, no problem, size. We should every time classify the structure according to the type and the size, except for massive and single grain structures. You can find here the single grain and the massive structures. So if you classify the soil horizon, the material, the layer, without a structure, without a type of structure beyond the single grain or a massive, we should classify a size. But if you have this one or this one, you shouldn't classify a size. You don't have to classify a size because these materials, they don't have pads, they don't have aggregates. So how can I measure something that doesn't exist? So single grain and massive structures, they don't have a size. We don't have to measure the size, but all other structures, all other shapes, we should describe, we should classify the size of these pads, okay? It's quite easy. You just need to measure the diameter or the thickness of the material, okay? So you have a platy material, something like this. You just need to measure the thickness of this material. So, okay, they have something like 3 millimeters, and I can see that they are a platy structure in a medium size, okay? A platy shape, a platy form in a medium size of this structure. Okay, so first of all, you should describe the type, and after that, you should describe the size of this structure. And in the end, you should describe the grade of the structure. What is the grade? It's the reproducibility of the aggregation, the pads. First of all, we should classify as a structureless materials those horizons or layers that has a single grain or a massive structure. So again, if you have a single grain structure or if you have a massive structure, you don't have a grade. You are just structureless. So you don't need to measure the grade if you have a single grain or a massive structure. But if you have any other shape, any other type of aggregation, of type of aggregate, a pad, you should describe them between weak, moderate, and strong grades. The weak grade is the first one. It's when you have a low volume of pads and a huge volume of material without aggregation. So you can see that the formation of pads are weak. The formation of pads are incipient. We don't have a lot of pads for a specific volume of soil. We have a strong grade if you have a huge volume of pads and a little volume of material without aggregation. So just a few volume of soil are not formatting, are not clustering in pads. So the formation of pads are strong, are developed, okay? Generally, we said that these soils, these horizons, they are developed or well developed, okay? Because we have a strong aggregation. The soil formation factors, they act to create a strong grade, and they interact between them very, very intensively. So they create a strong grade. And if you have something like half and half of material without aggregation and with aggregation, something like this, you have a moderate grade. That's what we found usually is the most common case, is the most common grade that we can identify is the moderate grade between weak and strong. Quite commonly, we can find weak grades in soils that are quite incipient, like candy soils, leptosols, fluvisols, regosols, antisols, soils that are not so evaluated, are not common to be found in tropical and wet areas. Oh, just a moment. Someone asked me to enter in a class. Just a moment. Okay. Okay. So we can find a weak structure, a weak grade in soils that are incipient. And we commonly found them in very steep areas where the slope favor erosion. So we have a lot of erosion, soil loss, okay, high runoff, and arid or semi-arid climates. And a low vegetable cover. Oh, cover, I'm sorry, cover. So we don't found a lot of vegetation or dense vegetation here. Someone asked me something, just a minute. Let me see. Oh, it's a good question. What about compactation? It's very interesting question. Thank you. Usually we found compacted soils in this situation and this situation. Why? Because this situation, they helps a lot formation of porosity. So we have a lot of exchange of air and water, a high conductivity, a high infiltration and of water. So compacted soils and naturally dense soils, we usually found this kind of grades, weak or moderate, and sometimes the structureless grade too. Okay, if you compact a soil, if you destroy the aggregation, you can create or you can change a strong grade to a moderate or even to a weak grade. Okay, because you stop the formation of pads and you start the broken it, you start destroying aggregates, so you start to release material like sand, silt, and clay are not forming aggregates. Okay? And in an opposite condition from the weak grade, the strong grade, we usually found in tropical and wet areas. And we can see something like a savanna or a rainforest covering this area. Okay, so it's very, very usually to find this kind of vegetation here, like in savanna or in Africa, or the Brazilian savanna that's quite similar, or the rainforests that we can see in several countries. Okay, we can find this kind of structure because the vegetation cover, the roots, and the activity of animals, they help the formation of a strong grade because they create a lot of voids and they help the formation of strong aggregates, strong pads, and they create a strong grade 2. And in this case, it's just intermediate case between a weak and a strong. So we can find this kind of grade in several areas, but this is quite common in semi-arid and arid conditions with low vegetation cover, and this if you have a lot of water or today or in the past, and a dense vegetation cover, okay, or a dense biological activity. Okay, another thing, another criteria that we have to describe is this consistency, and the consistency of soil. They help us to understand how is the behavior of soil in dry, in moist, and wet conditions. So how is the behavior of soil when it is dry? It's very hard, it's extremely hard. Think that you are a root and you need to grow up, and you need to penetrate in soil. Or think that you are a termite and you need to borrow some soil and create some channels. Can be easy or can be very hard, depending on the consistency, of the material, of the soil, of the layer, of the horizon. Okay, and we need to measure it in dry conditions, in moist conditions, and wet conditions. Okay, it helps a lot. It's quite important, especially if you work in a field that you interact the vegetation cover and the soil properties, because it helps a lot. It helps a lot to understand how vegetation could be favored or the vegetation cover can be avoided in an area, okay, according to the consistency of the soil. And the consistency of the soil, it is influenced by soil texture, so the content of clay, silt, and sand, especially sand and clay particles. They influence a lot the consistency of the soil, the consistency of the horizon or the layer. They are very different particles that influence a lot of the consistency, okay? And of course, the clay activity. If you have high activity clays or you have a low activity clay, you have different consistencies of the soil horizon, okay? JJ, I don't remember what is a high activity clay. It's quite easy to identify a high activity clay. These clays are those that we have 2 to 1 minerals. So we have expensive minerals. So they are materials that suffer a swing and shell process according to the humidity of the soil. So if you have a lot of water or if you have low water content, the soil, they will suffer a swing or swell process. And this is a high activity clay. And the low activity clay are those materials that has 1 to 1 minerals or oxides, like iron oxides, manganese oxides, aluminum oxides. They don't suffer shrink and swell, or just a little shrink and swell process. So they don't expand a lot. They are not expensive minerals. Okay, so here we found soils that has a lot of goethite, hematite, kaolinite, and here we can identify smectite, light, and several other materials. These kind of clays generally are formed in incipient soils, formed in semi-arid and arid conditions, climate conditions, or a parent material that was exposed at just a brief time, just like 100 or 1,000 of years before the present, and the climate and the organisms, they don't help intense deeply weathering and leaching of these materials. So we keep a high activity of clay, and the low activity clays we can found in well developed soils, in wet and tropical climates. So here we can find some alphisols, we can find some vertisols, some cambi soils, some insect soils, some ribosols, and here we can find some oxysols or ferrosols, ultisols, and others. Okay. And if we start the description of the consistency with dry soil, we should measure the hardness of the material, the hardness of the soil horizon or soil layer, okay? And how should we describe the hardness of soil of a horizon? We should use our index finger and the thumb finger and press the pad, press the aggregate here. So I should put some power here and some power here, just pressing these two fingers in a vertical way, and I will measure how easily can I broke this pad, this aggregate. How can I destroy this aggregate, okay? So if I just try to catch the aggregate and I already broke it, that's a loosey hardness. It's a loosey consistency. It's quite easy to broke if, okay? If I should put some power here, but it's quite easily, I can easily broke this. I have a soft consistency. If I should put some strength here, some power here, I can find a slightly hard consistency. If I put a lot of energy, a lot of power here, and I broke this aggregate, I have a moderately hard consistency, okay? If I put a lot of energy here between my index and thumb, and I can't broke this pad, I can have one of these materials. So all of this, they are broken by index plus thumb pressure. Okay, so if I put some energy here and I can broke the pad, they will, some of them, if I have just a few energy, or if I put a lot of pressure, I will change these classes, okay? If I can't broke with my index finger and my thumb, so I should classify between them. If I can't broke this material, this pad, this aggregate with just these two fingers, I will use my both hands. So I just need to catch the pad with my two hands, and I use this movement. So I will catch with one hand here and one hand here, and my pad is here, okay? So I don't have, I'm not a professional in drawing, but you can see it's one hand, right, and the left hand, okay? And I use just this movement, like I will try to flexure my material, okay? Trying to putting some pressure here, like just doing this movement, okay? Like I'm trying to broke this with my two hands at the same time, okay? If I easily broke my pad, my aggregate, using my two hands, it has a hard consistency. If I broke, but not so easily, it has a very hard consistency. If I use a lot of energy, a lot of pressure, and I can't broke, I'm sorry, my material, it could be extremely hard, rigid, or very rigid. If I use a tool that easily broke the pressure or the pad, I have extremely hard consistency. If I use a tool like a hammer and I can broke my pad, but it's not so easily, I use a rigid consistency. And if I use a tool, and even using a tool, I can't broke my pad, my aggregate, I have a very rigid consistency. So again, if I can broke the pad with my using only my two fingers, my index and thumb, I should classify between these four classes. Easily, not so easily, not so hard, and hard. Hardly I can broke with my index and thumb. Okay, here, if I can't broke using index and thumb fingers, so I should use my two hands. And in this case, I can broke using my two hands easily, not so easily. I can't broke with my two hands, so I use a tool. Oh, sorry, tool. No, it's two. Oh, sorry. Using a tool, so it's easily broken. It's not so easily, and I can't broken even using a tool. So we can use this kind of organization of description of criteria to describe the consistency of the material when soil is dry. And this is quite important to us. Why? Because think, if you are a plant, you are a vegetable, and you need to grow your roots. Should we choose an area to grow up? And if you can choose, we'll choose a loosey or softy area, something like this, that's very easily, the pads are easily broken, or you will choose something like this, that's very hard to broke. So the roots are very hard to grow up in the soil. It's very, very difficult. So soils that has this kind of consistency, they generally, they don't have a dense vegetation cover because naturally it's hard to grow up there. Okay, and the animals, they don't use to burrow in these areas because it's also very hard. You should use a lot of energy to create a hole to dig here. And here it's very, very easily. So they generally, they prefer this kind of materials. Okay. And also we can identify this loosey consistence. They are typically to sandy horizons. So it's typically from horizons or layers that has a lot of sand. Soft consistence are typically from horizons, or soils, or layers that has a lot of soil organic matter. So the soil organic matter content is high because soil organic matter favors a soft consistency because they create a kind of cementation that are not so hard but soft. If you press some material that has a lot of organic matter, like my finger, my face, there's a lot of organic matter here, they are quite soft. So you can think that a soil or a horizon that has a lot of organic matter, they could be soft. Okay. Materials that has a slightly hard or moderate hard consistency, they generally are rich in 1-to-1 or oxide minerals. Okay, so they are deeply weathered soils. And materials that has this kind of consistency, they have a lot of minerals that has a 2-to-1 minerals, and they are incipient soils, or no, not so deeply weathered and leached soils. Okay, so we can identify a lot of properties only describing the consistency of a horizon of a soil. Okay. We should describe the consistency when it is moist, and I'm sorry, it's not hardness, so let me change this. Sorry. No, it's okay. When we describe the consistency of the material moisty, we should describe it is friable or not, and firm or not. Okay, so again, we should use the index and the thumb fingers, but we should get moist, the soil moist. Okay, so we put just a few water content below the water capacity, the field capacity of soil. So we just put a little moist structure, a little moist pad, a little moist unit, just put a little water content, and we will pressure this material. So we pressure this material dry in a dry situation, and again, we will pressure this in a wet, in a moist condition. I'm sorry, just a little water, okay? Just to measure the color in a moist condition. So the material, they can't has a lot of water. We just need to feel that all the water that I add in that pad, it just was absorbed by the soil, and the soil not lose water, not losing water, not a fluid condition, are just a few water content. Okay, and we will now pressure again. Just put some energy here using my index and thumb fingers, and if I easily can broke my pad, my aggregate, I will choose a loosey consistency. If I can broke this material very easily, I will try now to press the material using my hand. So all that material that was broken, using my two fingers, I will put in my hand, and now I will pressure this material with my hand. Okay, if I pressure this material and this material, they don't get together, they are not just loosey, so I will choose a loosey consistency. If the material is easily broken using my two fingers, and I pressure this material with my hand, and I can see that this material start to get together again. So when I pressure this moist material, the particles get together again. I have a friable condition, a friable consistency. And if I easily broke this material using my fingers, and when I pressure this material, when I put press with my all using all my fingers, and all the material get together like this, you can see that all loosey soils that was produced by breaking this pad, they are together right now, just using all my hand, just making this, just pressuring my hand. So I have a very friable consistency. Okay? So again, If I can broke the pad, the aggregation, use my index and thumb fingers, I should choose one of these three classes. If the material don't get together again, when I pressure in my hand, we have a loosey consistency. If some of the material get together, but it's not all the material, we have a friable consistency. And if all the material get together, we have a very friable consistency. Okay? And all of this, I can't broke this with my fingers. Okay? If I can't broke my finger with using my fingers, again, I use two hands trying to broke this in this movement, flexuring the material. So again, I use one hand here, and I use another hand here, and I will put the pad here, and I will use this movement like flexuring this material. And I will try to broke this using my two hands, trying to broke the aggregation, the aggregate, okay? If I easily can broke the pad, it is classified as a firm consistency. If I can broke the material, but it's not so easy, I have a very firm consistency. If I can't broke the pad using my two hands, I can have one of these three classes. So again, I will use a tool, and if I using a tool, I can easily broke my pad. If I use a hammer and hit the material and it is easily broke it, so I can have an extremely firm consistency. If using a tool, using a hammer, something like that, it's quite hard to broke the material, so I have a rigid consistency. And even using a tool, I can't broke that material. They are very, very hard to broke it, so I have a very rigid consistency. Okay, and again, I can found that description. If I have a loosey consistency, I have a soil, a layer, a horizon that has a lot of sand. If I have a very friable or friable consistency, I have a 1-to-1 or oxides minerals. Okay. If I have this consistency, so I have a 2-to-1 minerals. Okay. So it's very interesting. It's very useful to us, the description of the consistency of the material. Okay, it's very useful to everyone because it helps a lot to understand how is the behavior of soil, and the behavior of soil helps a lot to understand how it is formed, which minerals can I identify, and how vegetation and animals interact with soil particles. I also should describe the wet consistency, or the soil, the behavior of soil if it is wet, okay? And when I have a wet condition, I should describe using two criteria. So I should describe the plasticity of the material, I just need to broke all the particles here. So I put a lot of water in my hand and I smash all the soil and I create this material, like this tube of soil, okay? And now I will describe how the particles are absorbed to each one, how they interact. If they interact very strongly, I can have a very plastic or a plastic consistency. And if I don't have a high interaction between the particles, I can have a non-plastic or even a slightly plastic. So if I put a lot of water and I broke all the material in my hand and I can't create this kind of tube because soil is very sandy, I have a non-plastic consistency. If I can create this tube or they are easily broken, I just start to move to create this movement and they just broke it. It also is classified as a non-plastic consistency, okay? If I can create a tube and I try to just catch and put against the gravity, or it just broke very easily, or if I just try to put this and this points together, if I try to connect this tube, you trying to make a circle and it breaks, it cracks, I have a slightly plastic consistency, okay? If I try to put these 2 points together, if I try to connect this tube and it didn't crack, it didn't broke, I can have a plastic or very plastic consistency, okay? So it didn't or don't broke when I try to connect this tube, okay? And if I try to make something like this, I have this tube, and I try to connect this point and this point, so I make something like this. And I can't see cracks here. Okay, it could be a plastic or a very plastic consistency. So now I try to make something like this. I will try to put like this movement. So I create a lot of curves and I see some cracks here or here or here or here. So, okay, the material is broken. I can see some cracks, but only when I create a lot of curves, so the material has a plastic consistency. And if even using these materials, like I can put a lot of curves and the material don't crack, the material don't break, I have a very plastic consistency, okay? So the plasticity, they just are measure the how this material, how these particles, they interact between themselves when soil is wet, okay? And of course, here is to sandy textures, sandy materials. Here, it's quite common to one-to-one minerals and oxides, rich minerals or rich horizons, rich layers. Some of this plastic we can find here too, but if I have a lot of clay, I have a clayaic horizon, so I can have a plastic consistency even if I have just 1-to-1 minerals or even oxides, okay? But I have to have a lot of clay, something like 60% of clay or 80% of clay, a lot of clay. And plastic and very plastic, I can usually found in 2-to-1 minerals, especially this one, especially the very plastic consistency. So I can understand that the plasticity, they express the texture again, and which kind of minerals I have in a clay fraction. How is the clay fraction? Even I can describe this in the field, and I can see, okay, this soil has a lot of high activity clays. So this soil was formed in a semi-arid or arid conditions, or the material was exposed like 1 or 2 hundreds or thousands of years. It's very new landscape here. It's not so deeply wet condition, okay? I can describe just describing the plasticity. Some of these analyses I will do in the lab again, but the description in the field helps a lot to understand how could be these results and what should I expect from this analysis, okay? Oh, it's just a picture when I'm trying to make this whole material, this picture, when I'm trying to connect these two dots, okay? And we also measure the stickiness of the material. And the stickiness is how the soil, how the particles, they adhere, they interact with another object, with another material. And so how soil interact with another material. And in this case, we use our hand. So my hand, they are very sticky with this material or not sticky with this material. So again, I just need to put a lot of water, broke all the pads, and now I will just need to pressure this material using my index and thumb fingers again. And I will measure how hard it is to separate my fingers. So if I just can separate my fingers very easily because the material are not stick, they are described as non-stick consistency. Quite common to sandy materials, sandy soils, sandy layers, okay? If I feel that I can individualize my fingers, but it's not so easily, I can describe it as a slightly stick horizon, a slightly stick layer, okay? If I can hardly individualize my fingers, individualize my fingers, if I can hardly separate my fingers, it could be sticky or very stick consistencies. If I can separate my fingers and I feel just a little pressure trying to keep my fingers together, it is a sticky consistency. And if I feel a very resistance to separate my fingers, so material starts to get together with my fingers, and they shouldn't, I can't separate my fingers very easily, I will describe it as a very stick consistency. So again, these two consistencies are typical to 2-to-1 minerals, and this is typical to one-to-one minerals and oxides, and this is typical to sand materials. So again, if I describe the consistency of my soil, I can know how is the behavior of soil. And this, specifically this thickness is very important, because think if you need to build a road, and if you choose something like this, a stick or a very thick material, probably you have a lot of problems if it starts to rain in a sticky or very sticky road. But if you have a non-sticky or slightly sticky road, okay, it's not a real problem. Here in Brazil, we have a lot of problem with this in an Amazon rainforest, because they grow a lot of roads and sticky, very sticky materials. So if you think that Amazon rains a lot and you have a sticky or a very sticky soil, is not a smart option to create a road there, because it's quite hard to drive in these areas when it starts to rain and rains a lot. So it's very important to describe the thickness of the soil, so we can choose specific land uses that could be useful in that area, and some that's not so useful. Okay, the thickness and plasticity are very interesting to describe how the human colonizate an area too, because if you have a non-stick soil and non-plastic soil or non-plastic horizon, usually you can find some artifacts, some materials that was produced by men. So some areas that are very sticky or sticky structure or consistence, I'm sorry, you can found a lot of materials that was produced by man in the past. So you can measure when the humans start to colonize an area using these materials. So it's very helpful to understand also how men and women colonized an area in the past. Okay? Okay, we have another properties that we should describe to, and some of them are the surface features, that are features created or formed in the surface of beds and voids. Okay, so if we saw a bed, and we should describe the type or the shape, the size, and the grade of the structure. Okay, so now I can see only the type, and in the surface of this pad, of this aggregate, how is the surface? The surface has any kind of coating, and typically the most abundant coating is clay bridges and clay films. So generally we can find the surface of beds with a lot of clay films. They are usually called argillons. So we can describe these materials in the field. Okay, but we have a lot of kind of coatings, like we can identify some carbonate coatings, silica coatings, gypsite, iron, gypsum, manganese, organic coatings, sand coatings, a lot of materials. Okay, so we should describe which kind of materials that we have in the surface or inside a void. Okay, I will show you some examples here, like this one. It's a shiny surface. It's very beautiful to describe them because you saw a pad that has a shiny surface. So it has a lot of clay particles, like some thousands or many thousands of particles of clay in the surface that create this shiny surface because the coating of clay. Okay. And also see this, you can see that it has a shiny surface. Here it's very easy to see that because here we have a surface that doesn't shine, and here we can see a shiny surface. In the same pad, in the same aggregate, we can see some shiny surfaces and some that doesn't have so shiny surface. So this behavior is not so common, but it present in some places, in some areas of this pad. Okay. And here again, we can see some shiny surfaces. And the process of formation of these coatings, it's very interesting. So every time that you saw a shiny surface like this, or this, or this, you should understand that in that soil, we have clay eluviation. We have migration of clay through soil. Okay, let me show you how can we understand this. Just a white slide like this. Think that we have a soil profile here. Okay, and here we have an A horizon, a E horizon, and B horizon. Here, C horizon. Okay, in the A horizon, we have mineralization, the main soil formation factor. That's the mineralization of the inorganic material. So we have a low velo and low chroma in these materials because the decomposition of organic matter starts the mineralization of inorganic material. We have the E horizon that's formed by eluviation, the migration of materials, of organic and inorganic materials from this horizon to another horizon. And B horizon, one of the soil formation facts is the accumulation of clay. So the eluviation, alluviation. And when clay migrates from here to here, the clay migrates through soil voids. So if you saw this, you can understand, you should understand that. Just okay. Okay. You should understand that. Let us draw some voids here, something like this. Okay, try to understand that this is a void, and this void are formed in a wall of pads, of aggregates, okay? So we have some aggregate. Oh, let me draw in another way. I think that could be easier to understand. Just a minute, okay? Okay, no, I think that could be easier. Let me draw some aggregates here and here and here. Okay. You all know that I'm not an artist, so my draws are not so good, but I'm trying. So imagine that these are aggregates in the soil, okay? And when it rains, the water, they migrates through a horizon, and migrates between the pads and always migrates in the voids between pads, okay? And the velocity of water is high in the surface horizon and the E horizon because we have the gravity potential and because we have a lot of sandy here. So we have sandy horizons and or we have a lot of gravity potential that induces the migration of water, okay? Here in the B horizon, the gravity potential is not so high. Generally, we have the tidal water here between B and C horizon. So water didn't migrate downward here, just from here, the surface to this place, this staff, okay? So the velocity of water is not so high. And when water, they migrate between this curved voids, they reduce the velocity. So water starts to migrate in a very low velocity. So when you decrease the conductivity, the velocity of the water starts to deposit clay in a surface of pads. So imagine this pad in here. When water start to migrate this and they used to do these curves or here, the decrease of energy of the water helps the accumulation of clay. So if you have elevation, if you have migration of clay with water, every time that you decrease the energy of the migration of water, you induce the alluviation. You induce the deposition of clay in a surface of a pad, of an aggregate. So every time that you decrease the energy of water that migrate through soil, you increase the deposition of clay in the surface of beds. You increase the alluviation. So you increase the clay coatings. So the decrease of energy of water that migrates from surface horizons to subsurface horizon, it helps to alluviation. It helps the creation of clay coatings in the surface of pads. And these pads, they just shine because it has a lot of clay particles deposited in the surface. And generally, this clays has this shape, and this shape is very useful to reflect light. So if the sunlight incides in this surface, they are just reflected and create this shiny surface. So when I have clay migration, I can see this kind of shiny surface because clay, silicate clay, okay, clay minerals, they create this shiny surface because they has a platy shape, okay? If I have migration of organic matter and or oxides like this, if I have here A horizon, E horizon, a B horizon, and a C horizon, and I have migration of water, and water, it carries organic matter as clay in a clay size, okay, or oxides like iron or manganese or even aluminum oxides. They don't create a shiny surface. They create opaque surfaces. They create surfaces that are dark, are not shiny, okay? Even organic matter or these oxides, they create dark surfaces. So migration of clay always create something in a surface of pads or the filling of voids. Depending on the kind of material, for clay or silicate clay, specifically silicate clay, you create a very specific surface features, okay? If you have migration of carbonate or silica or gibbsite or manganese or organic matter, you have different surface features, okay? It is very important to understand that if I have migration of E, B, oh, it's not good. If I have A, E, B, and C. If I have migration of organic or oxides, I don't have shiny surfaces, I have dark surfaces. And if I have migration of clays, specifically clay size minerals or clay minerals or silicate clays, I will produce shiny surfaces, okay? So they are very different. You can see here. So these surface features, they help us to understand how some soil processes act in that area. And the elevation of organic or inorganic material, oxides, or silicate clay, they usually occur in wet conditions. Oh, here to here. They usually occur in organic, no, in wet conditions and soils that has a lot of gravity potential. So these soils are above the sea level, okay? And if you have carbonate coats, you have dry conditions, you have a semi-arid or arid climate. If you have sandy, silt, or skeleton conditions, you have dry conditions too. Okay. So, but in this case, in carbonate or silica contents, in these coatings, you have some specific conditions like high pH, high content of carbonate, like the soil are formed from limestone, something like that. And in this case, we have a lot of sand or silt content. So the soil is formed from sandstones or siltstones, or the weathering is very, very incipient, very, very low. Okay. Here we can see some of these features in a microscope, like this white zone with PL symbol is a void, okay? And we have this dark material here, and this dark material is just clay that was deposited in the surface of the pads, in the surface of the voids. So even in a microscope, even when I'm not in the field, I can see some of these features that help us to understand, okay, if I have clay here, it's because clay migrates through soil voids. So I have a migration, I have elevation of clay, and I can analyze which kind of clay. Okay, they are oxides, or they are silicate clays, or they are another thing. Okay, like this. These crystals are formed by calcium carbonate. So they help us to understand that in an incipient condition, I have in the past a migration of calcium carbonate that was deposited in the void, and after that I have another eluviation process that migrates clay, and this clay, this oxide or this silicate clay, are deposited in the void too. They are overlaying the calcium carbonate layer. So we have two eluviation process. One in a first time of calcium carbonate, probably in dry conditions, and a second one of clay, probably in wet conditions. So the same soil profile has two eluviation processes that that occur in different climate conditions. So I can understand how soil was formed very easily just using this picture. It is very useful to understand that. Oh, this picture is very easily too, because I can see some pads here. Okay, and we can see some material overlying this pad, some like here, some like layers above the aggregate. Okay, so it helps us to understand that clay is migrating or migrated in the past through soil profile from the surfaces to the subsurfaces horizon. It's very useful to see too. In a microscope, we can see some quartz grains like this and this, all this white and gray white grains are grains of quartz. And we have some dark and yellow dark materials that help us to understand that we have a little migration of clay in this horizon. So a little deposition, elevation of clay from the upper horizon to the horizon. So we can identify a little of clay migration, maybe incipient condition, an incipient soil process. Here we can find also this condition. Here we can see some migration and deposition of calcium carbonate here. So we have this fragment of rock, this material, okay, all this material. And here we can see some deposition of calcium carbonate. And it's very beautiful because we can see several layers. So we can understand that we don't have just one moment of migration and deposition of calcium carbonate. We have several, and we can even dating these materials and much time spent in forming this surface, this pedal surface features, okay? And we can see some stress features too, okay? Some features that are not formed by clay elevation, but by shrink and swell process. So if soil soil has a lot of high activity clays, it suffer a lot of expansive movements and retraction movements. These expansive movements, they can create some stress features. You can think in this way. Think that you have a soil here, okay, and in this horizon we have this prismatic features, okay. Let me just put them together, closely together. And so one is here, and another one, it's very close, okay? Okay, so the soil is dry and they retract everything, so the pads are very, very close to each other, and starts to rain, and when it starts to rain, this material that has a lot of 2 to 1 minerals start to shrink, and we can see the expansive material, and this pad starts to expand to all dimensions that you can imagine, but this pad also start to expand to several dimensions. So we have some zone here that has a lot of stress because it has a lot of pressure from this and this pad. So this zone start to have a lot of pressure, because we have some expansion from here and from here, and this zone, there's a lot of pressure, and this pressure start to create a shiny surface, not by migration of clay, but only because of the pressure. And we can see some shiny surfaces like this one, okay, in these materials. And it was not created by clay alluviation, but only by pressure, okay? We call these stress features as lichenites. So these lichenites, they are formed by pressure, only by pressure, formed by 2 to 1 minerals. Horizons or layers that has a lot of 2 to 1 minerals. Minerals that has a lot of high activity clays. So some vertisols, some utasols, they has a lot of lichenites because they have a lot of pressure faces. Okay, and it's quite easy to differentiate the pad surfaces, the surface features that are formed by alluviation and the features that are formed by pressure, because the features that are formed by pressure, you can see something like this on lines, like these ones, that show the pressure of these materials, because they are formed by pressure of these two aggregates. They are not formed by only the position of the material. So the surface features are formed, the clay coatings are formed by calm water that deposit clay in the surface of the pads. And the stress features are formed in stress conditions, are formed by pressure, high pressure of these surfaces that create these shiny surfaces. Okay? Someone has any question? I heard something. No? Is it okay? Okay, okay. So again, the stress features are formed by pressure of the faces of these pads that creates a shiny surface, but a shiny surface with a lot of lines like these ones that we can see. Okay, and these are typical to 2 to 1 minerals, layers and horizons that has a lot of high activity clays. We can see this kind of structures in materials that has 1 to 1 minerals or oxides. So uh, we can find some stress features, some lichenites in oxysols or ferrosols or soils are not common because the soils has too much content of 1 to 1 minerals or oxides, and we just can't find 2 to 1 minerals. So we can't find smectites or lights or another materials that induce shrink and shrivel of the horizon, shrink and shrivel process. Okay, so stress features are formed by pressure of the faces of a bed, and coatings, bed and void coatings are formation by illuviation of water and clay. And this clay could be organic clay or inorganic clay. Okay, are very different conditions, but all of them are surface features. Okay, um, has Let me see if I, oh, okay, this you can see again a shiny surface here with a lot of lines showing this stress formation like this, okay? These features are not so common in Brazil, and I think that are not so common in Africa too, but we can find some areas that there's a lot of these features, especially areas that a lot of clay and high activity clay, okay? And anyone has a question? Has anyone a question? Everyone understand everything that I said? Oh, let me see. I don't know if I have a question. Oh, it's a very good question, Kenneth. These properties are very connected to fertility and acidity or alkalinity of the soils. Let's show how can we connect some of these properties, okay? Let me put in this way. If you have this kind of consistency, loosey, soft, slightly hard, or moderately hard, generally you have low pH, so you have a lot of acid, and you have acidic soils, and the fertility, the natural fertility is not so high, so probably the base saturation will be low too, okay, the base saturation. And if you have these kinds of consistency, the dry consistency, generally you have a high pH and a high saturation of bases or base saturation, okay? So the natural fertility, it's high, but you have physical problems, because if you try to put some materials here, if you try to put some vegetables that has fragile roots, are very hard to use this kind of soil. So depending on the kind of land use that you want, could be better choose acidic pH and a soil with a low content of bases, because you can put some nutrients, you can correct the pH, you can increase the pH, but hardly you can manage these conditions. Like if the soil has a rigid or a very rigid consistency when dry, and you are working or you live in an area that you don't have a lot of rain, it's quite hard to use this soil, because every time or several months of a year you have a rigid or a very rigid consistent, so the root growing or the land use, it's very hard, okay, because you need to put water to help to root to grow, but you don't have a lot of water. So depending on the use that you are thinking, maybe could be better choose something like this, okay? And the moisture consistency is the same. So if you have some of these classes, you have a high pH, or at least a not so high acidity, okay? Something like 5 to 0.6 to 6.5, or at least 7, or even 8 pH, 8 value, okay? So you have high pH and a high base saturation, maybe 80% or 90% or even 100% of bases that occupies the complex cation exchangeable, okay? And in this case, we have an acidic pH and a low content of base saturation. In this case, again, this low fertility, low natural fertility, and here are high fertility. So maybe this could be useful, or this could be useful. If you are thinking in a region that rain, but it's not so wet, you can prefer this kind of consistency because helps to work. It's not so plastic, so the compactation is not so easy. If you try to use some tools, maybe you can compactate the soil if you have a plastic or a very plastic consistency. So if you have some of this consistency in wet conditions, could be better. And if you have dry conditions, maybe this could be better. These conditions, you have high pH and high content of bases, of nutrients, and here you have acidic pH and low natural fertility. Thickness is the same. In this case, you have a high content of bases, of nutrients, and generally a high pH. But if you have wet conditions, if rains a lot, you have a sticky or very sticky surface horizon. Could be very hard to use the soil. The management of soil is not so easy, so maybe this could be better, okay? Because even in wet conditions, the soil are not so heavy because it's not so sticky, so you can use some tools that helps a lot to use the management of the soil. And these surface features, they don't help a lot to understand the fertility, the natural fertility, but generally we can find these materials, these pressure phases, in materials that has a high pH and a high base saturation, okay, a high saturation of bases, so a high natural fertility. But it's also hard to use because you have physical problems, like think that you are root of a vegetable from leaf, and the shrink and shell process start to broke your roots, so the vegetables doesn't like very much to grow up in places that you have stress features, because all the time during the dry and the wet seasons, the roots are always being broken by the shrink and shell process, okay? So depending, always depend the land use that you are thinking, or the environment, the climate conditions that you have, or if you can irrigate, if you can put insect water, so you can choose the land use, okay? We will discuss about this in the future. Anyone? No? Everyone is okay? Is everyone
Yes,
okay?
sir. We are okay.
Oh, thank you, Aminu. So People, on this week, I will try to share if with you another video, another recording with our classes. Okay, I will try to do this in the Tuesday or Friday. Okay, because in this Wednesday, again, we don't have a class because I have a meeting at the same time of our class. Okay, but I will try to put a video so you can see that, and if you have any question, you just need to ask me, okay, and by mail or in the next class. Okay, please try to finish the reading of the material, the references that I share with you, and in the next. Oh, sorry guys, I my Wi-Fi signer is very bad today.